Okay, I'll introduce our next speaker, Ashley Roach, from the University of California, Santa Barbara. Her field is structural materials. Advisor is Irene Bayerlein. And residencies are at Los Alamos National Laboratory in 2021 and 2022. Ashley.
Thank you. Okay, so hello everyone. So like many who have spoken yesterday, I did many things during my PhD, including some small-scale mechanical testing using in situ imaging in electron microscopes, as well as some magnetron sputtering of refractory alloys and some room temperature ductility screening of those alloys. But today I want to talk about some kind of more fundamental dislocation mechanics that I did during my time at UCSB, particularly relating to irradiation defects, nanovoids. So the general outline of my talk will be as follows. I'll touch briefly on why nanovoids are relevant in irradiated materials, on the current state of the literature on understanding the influence of these nanovoids and how they actually strengthen irradiated metals. I'll go briefly into my simulation approach using a Meso-Scale model, phase field dislocation dynamics, or PFDD. I'll be using that acronym a lot. And then I'll get into the results that we saw. So first, the actual strengthening trends of these nanovoids, what's actually relevant to application, and then getting into some of the mechanisms for why we see these trends. Spoiler alert, they're different than literature expects. So first I'll start with a little background on irradiated materials. So irradiated materials, metals in particular, often seen in nuclear power plants, but really in any case where metal is in the presence of irradiation, you will get irradiation defects. And so this is really important because, as you can see here, here's an example of an austenitic stainless steel, where through the depth of this material, you can see this really high density of black dots is what they look like here, but they're irradiation defects. And you can see this schematic damage profile showing that in a certain localized region of this material, you can have really high density of defects, and that can dramatically change the mechanical response of this austenitic stainless steel. So here's just an example of kind of the approach that people take to understand the strengthening effects of these high defect concentration areas, where you can look at, you can actually see an increase in both strength and hardening in these irradiated metals. So you can look at contributions from increasing your dislocation content. I'll talk about dislocations a lot. Increasing your dislocation loop content. You can have stacking fault tetrahedra, you can have bubbles, or we can notice here you can have nanovoids. Nanovoids are expected to be a significant contributor to the strengthening of these metals, in particular, increasing the bulk effective yield strength. So the current state of the literature is actually understanding the strengthening of these nanovoids by using a precipitate hardening analog. So we may be more familiar with precipitate hardening, where if we have a dislocation moving through our material, if it interacts with precipitates, shown here schematically as these circles, it will need to bow around these precipitates and eventually shear through them if they're weak precipitates. So we get to a critical bowing angle under an externally applied shear stress moving that dislocation. And some parameters of interest are, the material spacing between the voids, these edge-to-edge spacing, as well as the, center-to-center spacing between the voids, or the precipitates, sorry, as well as the actual size of the precipitates. So we can see that as the dislocation actually shears these precipitates, you can create a step on the surface. Here's a top-down view and a side view of creating, actually splitting that sphere, that precipitate, in half and creating a step on the surface. So this is kind of the state of the literature for understanding nanovoids. But I also want to point out that these consequences of nanovoids extend far beyond irradiated materials. Here's an example of a copper wire right in the necking region, so that shear instability right before failure, where you can see there's been a lot of deformation. Here's a micro shear band where just a lot of plastic deformation is happening. You can see within and around this shear band, there's a huge population of nanovoids in this copper, unirradiated, just as a consequence of ductile deformation. So I just want to point out that this has relevance far beyond irradiated steels. So now I'm going to get into the state of the literature as it stands. So before I go further, we saw some fantastic talks yesterday going over kind of the basics of dislocations, and I just want to touch base on that today and show a little bit about what I want us to take away specifically for this talk. So essentially, I've been saying dislocations a lot. They're the primary characters of plastic deformation. So when you deform a metal and it doesn't return back to the initial state, that's plastic deformation, permanent deformation. So there's kind of two states of these defects, these misorderings in the atomic structure of our metals. One is an edge dislocation here, which we had seen yesterday. It's schematically shown as an extra half plane inserted into our atomic structure. There's another case called a screw dislocation, where instead of inserting a half plane, we're taking two halves of our material and we're just slipping one, shearing one in relation to the other. And so the implications of these are broad. Again, they move through our material and transmit deformation, but they also have inherent stress fields associated with them. So our edge dislocation, our extra half plane, you can see where this half plane resides, we have local compression, and below it we have local tension. This is in contrast with our screw dislocation, where because we're not inserting anything into the material, we don't have that hydrostatic stress component. So these edge and screw dislocations are fundamentally different, even though they're both dislocations. So if we look at the slit plane where this dislocation actually moves through our material, if we look at it top down, we have our dislocation line, and we see that this net displacement, which is really, really important to transmitting that plastic deformation, is oriented perpendicular to the line of our dislocation. So as it's moving through, the net displacement that's transmitted through the material is perpendicular to that line. This is in contrast to our screw dislocation, where we have our slit plane here now oriented. This is where the dislocation line lies and where it moves through the material, where we have our net Burgers vectors oriented parallel to that dislocation. And so the angle between our Burgers vector and our dislocation line is called our dislocation character. And I'll be saying that throughout the talk, but just keep that in mind. That's the difference between edge and screw. And so I just want to point out, just to bring this back to reality, so each Burgers vector is only a few angstrom in length. So what we really see in metals is not a single dislocation moving, but we see avalanches of millions of them moving, and this translates to our macro scale deformation. So now let's get into the kind of state of the literature, how we understand this nanovoid strengthening in particular. So it takes a certain strength to move a dislocation through a material because it is that misordering of the atoms. It takes more strength to move that dislocation through an obstacle. So an obstacle in the presence of the dislocation will bump up the strength required to continue that plastic deformation. So what we do here is, in the literature, commonly people have our dislocation line. Here's an edge dislocation shown here. And what they do is, to understand this nanovoid strengthening problem, they align a periodic linear array of these nanovoid obstacles, all of equal spacing and equal diameter. And it's oriented so that our dislocation line, as it shears towards the obstacle, will interact with this entire line simultaneously. So we can understand the net obstacle strength of this. So again, geometric parameters of interest are, of course, our void diameter and this material spacing, S. So not the center to center spacing, but the actual distance of material in between the voids. So in the literature, when this dislocation shears forward and begins to bow around this obstacle before it can cut through it, there's a number of different forces that have been considered. So of course, we have our bowing angle, which is very critical and is expected to be related to our overall obstacle strength. We have our externally applied uniform strength that moves the dislocation. We have, of course, as we bow further and further out, the dislocation segments start to interact with each other. And this self-interaction can actually help move that dislocation forward as well. And then we have this image force, and this is a little complicated, so I'm just going to call it an image force. Believe me, we can talk about it after. I'm happy to explain. But essentially, when a dislocation is close to a free surface must remain traction-free. So because the dislocation has an inherent stress field associated with it, there needs to be some equal and opposite image force that maintains that traction-free boundary condition at that surface. And then we also have this kind of nebulous drag force that is generally used in the literature to quantify the energy barrier to moving that dislocation on that surface, because as we saw before, as we shear through the obstacle, we create a step on the surface. So creating more free surface has an energy penalty associated with it. So generally, the literature, we don't need to know much about these equations. I just want to show you that The kind of seminal work was from Scattergood and Bacon in the 80s, where we have our obstacle strength of our nanovoids is scaled logarithmically with our void geometry parameter. So this is a complicated mixture of void size and void spacing that they've called this D bar parameter. It's essentially a harmonic mean of D and S. And we can see also here that they have this scaling coefficient, this empirically determined scaling coefficient that has been added. Then Krohn, Munday, and Knapp came along in 2015, and they improved specifically upon how to treat this image force as well as this drag force in this problem, and they improved upon this model where we still have this logarithmic dependence on D bar on our void geometry, but they've changed it slightly, and we've removed that empirical correction factor. So just noting here, again, parameters of interest, our obstacle dimensions are this D bar, void size and spacing. And then material parameters of interest are our isotropic shear modulus, so related to the elastic properties of the material, as well as this Berger's vector, which is a property inherent to each material. Each material will have a different Berger's vector associated with it. So the general scaling trends are shown here for this Krohn, Munday, Knapp, or CMK model, versus our D bar parameter. And we can see on this semi-log plot that as you increase in void diameter, you increase in obstacle strength. But I want to point out that this D bar parameter is actually agnostic to whether it's D or S increasing. So this also translates, these dots translate equivalently to increasing S by the same amount. A little counterintuitive, and I'm not so sure is the correct approach moving forward. So I've kind of lured you in, and it's actually much more complicated, this dislocation theory. And so we're going to get a little bit more into what happens in FCC metals. So depending on the structure of your metal, you actually will have not just a nice straight dislocation line, but you'll actually dissociate. And so what this looks like, so I had talked about my Berger's vector, my shear step. So what happens is instead of having a nice shear step of moving this atom over here, we break apart this motion into two more manageable steps that are more energetically favorable. So we break apart into a partial dislocation where you can see we've changed the character. We've gone from being perpendicular to our dislocation line to at an angle, where we have a net partial step, a partial dislocation step, that is then followed by its complementary second partial step that completes this full Berger's vector translation. And so what this looks like in our material physically is we have now two dislocation lines called partial dislocations, separated physically by a stacking fault region. So this is where there's a fault in the stacking. This partial translation and then partial translation means that in between these two partials, we actually have a different ordering. It's no longer an FCC atomic ordering, it's an HCP atomic ordering. And this has, of course, an energy penalty associated with it. But it is more favorable to split up this shear step into these two partials. I also want to point out I've shown that we changed this dislocation character. We also lowered the line tension, the associated energy with this. So even though we've increased the energy penalty of having a stacking fault, we've lowered the actual line energy of the dislocation because we've lowered that Berger's vector step. So what does this look like for our nanovoid shearing? So instead of having a dislocation bowing around our nanovoid obstacles, it actually separates in space. So we have our leading partial and our trailing partial separated by this stacking fault width. So we can see that the stacking fault width can actually change depending on how you bow around this obstacle, and that's a really key point as we move forward. But we also change kind of the force balance of the problem. So now we have this stacking fault force that is working to decrease that energy penalty of having that stacking fault present, while simultaneously we had this elastic repulsion in between these two partials because we saw that hydrostatic stress component associated with an edge dislocation before. And so these partials elastically don't want to be close to each other. So it's this competing interplay between the stacking fault and the elastic repulsion, and each material has some set equilibrium distance. So again, the stacking fault width becomes a material property in its equilibrium state. But as you bow around your obstacles, you locally change that stacking fault. So I just want to point out that if this dissociated dislocation, as it's moving through, acts together and stays together very closely through the whole step, if we draw, if we look at our force balance here, we actually don't change anything because these will cancel each other out. So our force balance would remain constant. However, if our leading partial moves much farther forward than our trailing partial and interacts with that obstacle independently almost of the trailing before it reaches, then our force balance has now been changed. We have these additional considerations. And this is really the key result that we see in our results moving forward. So just to point out that large stacking fault width materials will have a higher likelihood of this leading partial moving forward and interacting with our obstacle before the trailing partial does, meaning that we change the problem. And so now analytical models aren't well equipped to handle this change, so we move to something like atomistics, molecular dynamics in particular. So now we can see that we handle this dissociation explicitly in our model, and then we again shear towards our obstacle. What we can see is here's a case of looking at both a BCC where there is no dissociation and an FCC where there is this dissociation, the stacking fault width. Where in gray, our BCC problem changing this D-bar parameter, the void size and spacing, we can see that it's bonded really nicely in between. This is the Scattergood and Bacon model with this empirical scaling factor for Orowan precipitates and voids, showing that our MD results scale relatively well with the analytical models. However, when we look at copper, which will dissociate, it possibly has a different trend. It doesn't follow these analytical models. So this really points us towards we want to figure out what's going on. So there has been some studies looking at that stacking fault width or stacking fault energy of dissociated materials, but unfortunately, molecular dynamics isn't well suited to handle a sweeping parameter study of multiple different materials because it's limited in reliable interatomic potential. So we have copper, we have nickel, and then that's just about it that we can be very certain these interatomic potentials are accurate. So what this one group did is they took a copper interatomic potential and artificially changed the stacking field energy without changing any elastic properties, no Berger's vector, everything else stays the same. And when they do that, we can see this kind of parameter space evolve, whereas you increase your stacking fault energy, which means that you increase the penalty of having that stacking fault width. And as we change the void diameter, we have these kind of two regimes. One is the single partial controlled, where one partial does move ahead separate from the other and interacts independently. And then there's a both partial controlled, where they stay very closely together and look more like the analytical model. And they saw that the overall obstacle strength increases as you increase the stacking field energy, as well as increasing the void diameter, but not necessarily following those analytical models. But this isn't the end of the story, of course. So we know very well that molecular dynamics is a very powerful tool, but it's just that, it's a tool, it's not the end-all be-all solution. So we're kind of limited in how we further explore this space. We are limited in small void sizes and cell sizes. We're limited in timescales because molecular dynamics is very high strain rate loading. And then we're also, again, limited in these reliable interatomic potentials. So we're limited in how many materials we can investigate. And because stacking fault width is a material property, we're limited in how we investigate the influence of stacking fault width. So in FCC materials, we still have unanswered questions. So this is motivating using our phase field dislocation dynamics, which I'm not going to go into. Please ask questions or come find me after. Happy to go into it. But this is an energetic framework. So we're familiar maybe with more phase field modeling. Phase field dislocation dynamics is very similar, where we evolve order parameters by minimizing total system energy by using the time-dependent Ginzburg-Landau equation. So we now look at our dislocations in PFDD, and instead of treating it like this misordering in our atom, we actually treat it as a boundary between slipped, where the dislocation has already moved and where that Berger's vector displacement has been applied, and unslipped, where we have yet to shear. And so we can look at, we can evolve our plastic slip order parameter in the same framework as we would in general phase field modeling, where we have our order parameter evolves to 1 everywhere that the dislocation has passed. We've used this before to look at voids previously in copper, where we can see here that we looked at unshearable voids that the dislocation cannot cut through, as well as shearable pseudo voids where we have infinitesimally small elastic constants associated with the free space of a void, and we can actually shear and cut the voids in this continuum framework, which is a really nice Meso-Scale approach to this problem that's still very heavily physics-based. So I'm going to step super quickly through kind of how we input the physics of a dislocation dissociation into this model, where we have this landscape, this energy penalty landscape in our slip plane. So as we move the dislocation through the material, there's an energy landscape that it has to move through. And we can see that, within our slip plane, if we move our full Berger's vector step, we have an associated energy penalty that we need to overcome, this generalized stacking fault energy. But if we move in our partial directions, if we split it up into two motions, then we have this associated curve where we can see a much lower energy penalty for our unstable stacking fault energy, as well as our intrinsic stacking fault energy, which is our material property. Just remembering that this intrinsic stacking fault energy is associated with that stacking fault width between the partials. So this enables us to capture dislocation physics in a continuum framework in this Meso-Scale model. So PFDD is useful because it gets us to larger cell sizes. Of course, this is a nanoscale problem, so it's still very small, but we can expand the parameter space for our investigation. We can also kind of remove this shock loading problem that we were having before that complicates understanding the fundamentals, because this is now a stress controlled motion where we apply an external stress and we evolve to equilibrium our energies. So we've removed that shock consideration. And we can also fully probe our material space. So we can look at full elastic anisotropy, we can look at material inhomogeneities, we can look at these gamma surfaces, and we can apply the same approach to a number of different materials equivalently. So we're not stuck with just copper and nickel as being reliable materials. So now I'll get into just very basically the setup of our model, where we have in our cell a dislocation dipole where we've colored, red is our slipped and blue is our unslipped, and we have this dipole here and we allow it to dissociate. And so now I've plotted this order parameter where we can see order parameter 0 unslipped, order parameter 1 slipped, and then intermediate, this white is our stacking fault region that we evolve. And this is just our Berger's vector decomposition, showing that this gamma surface has confirmed this expected decomposition. And then in this dipole component will move this way, this will move this way, and then in the path of their motion we put our obstacles, where again we look at our void size and our void spacing. We can also look at our material input considerations. So I've looked at 5 different FCC metals, and I've just shown here one line along the partial dislocation direction where we have overlaid all of our gamma surface obstacle landscapes for all of our 5 metals. And what I want to point out is all of these have different kind of energy wells at that stacking fault. Some of them more stable than others, and in particular, if we look at platinum here, it's a very unstable, a very shallow stacking fault well, meaning that there's a very actually limited drive to fully dissociate into these discrete partials. It more just spreads the dislocation core out and not having this nice discrete partial 1, partial 2. We can also, again, I say that this is a full material investigation. So instead of that MD study where we're just artificially varying stacking fault energy, we can look at anisotropy, elastic shear modulus, our stacking fault energy, our Berger's vector, and that stacking fault width. And I just want to point out that these 5 materials vary kind of incongruously from each other, where we have copper, very high anisotropy, medium stacking fault width, compared to something like silver that has also relatively high anisotropy, but also very large stacking fault width. So this is a nice combination of materials. And I further chose void geometries to span these characteristic like scales. So here's our stacking fault width range of our 5 materials. Just bring it back to real dimensions. Platinum is 0.5 nanometer, silver is 5 nanometers. And then I varied my void size and void spacing to span these. So our void sizes ranges from 1.5 to 7.5 nanometers. Void spacing ranges from about 1 to about 90 nanometers. So really, really expanding the probable geometries that we've been able to look at in comparison to MD. So I didn't go much smaller than about 5 nanometers or 5 Berger's vector in diameter, because if I go further than that, I get non-spherical voids. Not a problem, I just don't want to talk about it today. And I also want to motivate a new void geometry parameter that's different than that D bar that was agnostic to whether it's D or S changing. There's just this linear void fraction. So if we draw an arrow between center to center of our 2 neighboring voids, it's just a metric of how much of that line is void and how much is material. And noting here, relating that back to D-bar, we're just reducing the dimensionality of that parameter. And then this gives us a local obstacle density ranging from about 5 to about 70% void fraction. So now let's get into the results. And this is really the big exciting result, is that we see a remarkable collapse of our strengthening to this void fraction, this no longer D-bar, but this void fraction. And this holds for all materials and all void sizes. And we also see, of course, that there's no higher order D or S dependence. It all falls under this void fraction trend. And we also see a very strong mu dependence, this shear modulus dependence. So it's very dependent on elastic properties. So we can actually fit a scaling model to this. This is our linear fraction model, where we can see if we have our slope be just related to that stacking felt energy parameter, relating back to that gamma surface, then we can have very nice agreement with all 5 materials. And I also want to point out that this stacking fault parameter is very easily found for a wide range of materials. So this is a really applicable model. It also decently predicts our material rankings, material strength in relation to each other. So this linear fraction model that we've determined from this is very applicable and very useful. Comparing back to our, from literature, we go from a logarithmic to a linear dependence on void geometry. We don't have this additional dependence on characteristic length, and we don't have this higher order dependence on void size and spacing. We also, when we look at our scaling factor, we have this empirical slope dependent only on material properties, and material properties that are easily found for new materials. So I just want to end by bringing this back to our MD models, because we had shown that different trends evolve for FCC metals. And I just want to point out here that our linear fraction model is able to actually predict molecular dynamics trends as well. These trends just haven't been identified to date because they haven't been able to investigate this material and void size spacing space as we were able to. So I just want to show here in gray are plotted the molecular dynamics results for this pseudo MD study, where our linear fraction model trends remarkably well for low stacking felt energy materials, much better than literature. As we increase in stacking felt energy, our linear fraction model still is arguably the most accurate model, and then only at high stacking felt energy materials, which is much closer to our undissociated case because our linear and trailing partials are very close together, does the analytical model start to win out. So I just want to point out here back for application that austenitic stainless steels hover between these two cases, and copper is this case here. So with that, I'll skip ahead and kind of summarize what we've learned here and ask for questions. Oh, I don't know why this didn't pop up. Yeah. Yes, thank you.